Let me start by saying that there was a mistake in, I said the wrong thing in the talk, and I think also in the discussion, that the points in space-time, I said they would be given by subalgebras, self-conjugate subalgebras, which had dimension 2, and I should have said dimension 4. And I think this was repeated several times. I just hadn't thought about it for a while, and my memory had gone a bit confused on that one. Whether it works is not quite clear. I mean, it's certainly true in the flat space case that the points are represented by these self-conjugate dimension 4 completely commuting subalgebras. I should have said completely commuting. And the idea is that that would be taken over into the general case. But it certainly is again true that in the curve case, the points are represented by completely commuting dimension 4 self-conjugate subalgebras, but whether that's a sufficient characterization is something which is a guess at the moment. I think it could well be, but I don't know the answer to that. There are a lot of theorems which are missing in this whole topic, so I'm concerned here not with any theorems, because I think that's, when I mean theorems of existence theorems and uniqueness theorems and things like that, the only things that I use as theorems are sort of algebra things that you can just check by hand. Okay, now, this is slightly a recap, but the generating function I had previously for a symplectic structure, which is an obvious thing, so you have this symplectic form, which, at least on the null twistor space, works just as well for curved space as the flat space. It's the normal dp wedge dx that you have symplectic structure which carries over to the geodesics, and if they're null geodesics, that carries over too. So that symplectic structure is certainly there, at least when you have the scalar product between z and w being 0, and that's when you have null geodesics. And so you have that even in the curve case. But the idea is to extend this, take the symplectic form, extend it to when the scalar product between z and w is not 0, and this you can certainly do in lots of different ways, and you can extend the symplectic structure in lots of different ways. But there's too many different ways, so what do you do with it, you see? And so the idea is that having a generating function here for preserving this, you go from z's and w's to a different set of coordinates, if you like, or a different way of representing your space in terms of z's and w's. And this is the curly z's and w's, and you have a generating function, take one from one and the conjugate one from the other, and then z is d by dw, and the curly z is d by dw, and the straight w is d by dz. I like to have indices which would be different for, I've left off the indices just because it's really a different space when you're looking at the other, so you get confused by it, but never mind. You certainly have this, and this automatically preserves the form. This is all well-known stuff, what generating functions are for, and the idea also in this palatial stuff is that when you have this generating function, you can also use it to provide a connection on the well, it's just a circle bundle over the symplectic manifold that you have in the general case of the ordinary symplectic structure that you get from null geodesics and so on. Let's see, what was I saying here? Anyway, you preserve this, but also you can have a way of putting a connection on the it's the geometric quantization. I said this in the talk, so I won't repeat it here. But it's a way of getting the algebra, the non-commuting algebra, also out of the generating function. Yep. So the generating function preserves the symplectic structure. But also the specific generating function you choose is your way of splitting this form. Where have I written it? Yes, up here. As a D of a one form, and that particular one form it's a D of gives you a way of modifying your connection to one which respects a different symplectic, a different complex structure. Let me not go into that because that's things I did talk about in the lecture. But what I want to say here is the thing that I didn't have in the lecture, which was a way of preserving this other two form, So you have this two-form standard one, and then if you want the Einstein's vacuum equations, I was being puzzled by this because first of all I tried to preserve just the dz's by themselves, but what you want is this form plus the w thing. You get into a contradiction if you just try to preserve one or the other, and you find that you end up with only self-dual or anti-self-dual solutions. If you want to have a solution which is which is neither self-dual nor anti-self-dual, but gives you the whole Einstein-Landau-Vacuum equations, you have to preserve this form with the z's plus this form with the w's. And so I've written it here in the hook notation. This form with the z's is the dz hooked into the infinity twister. This one with the w's is hooked into the infinity twister the other way up. And the sum of those two is what you have to try and preserve. So the challenge here was to try and, with a single generating function, or somehow to make your generating function of a sufficiently special kind that it automatically preserves not only this form, but also this form. And this was the thing I realized how to do eventually. I'm afraid somewhat after the lecture I gave, but a few weeks afterwards. And here is the very strange trick that you need to perform in order to do this. Instead of choosing your standard coordinates, if you like, or standard representations of z's and w's, I choose this very peculiar combination. First of all, what's this lambda cross? Well, first when I did this first, lambda cross was the square root of lambda over 6. And then I realized there was a sign wrong when you try to make it real. And I'll come to that in a minute. But to make it real, it worked nicely if lambda was the wrong sign. That is to say, if it was if lambda was negative, and I don't want only to do it with a negative lambda. That might please the string theorists, but it doesn't please the cosmologists because we know lambda is positive. So it's really the square root of minus lambda, which is the thing that is this lambda cross thing. And the lambda cross comes in because you have to take the square root of this thing. But then the trick is you want to make these things come with opposite signs. And that has to do with the order in which you choose these coordinates. So I didn't notice this originally. Okay, now I choose coordinates that's combinations of z's and w's. They're all mixed up in this strange way. Lambda cross times z0, w1, z3, and lambda cross times w2. And those are the variables like the z's that we had here. And what are the curly ones from the other system? Well, I take, first of all, the straight conjugates of these. So this would be, if you take complex conjugates and forget about the lambda cross, this would go down to this one to this, and this, and this, and this to this. So you have this form, which one? This form here is still, if you write it in terms of these funny coordinates, these are still conjugate variables. Or let's just see, this collection and this collection are conjugate. And you can just check it. But the thing is that this peculiar combination also preserves the other form. So you just have to, when I say also, you have to make sure that your generating function gamma is symmetrical under the swapping of this pair with this pair, or swapping that with that, or with this, I should say, and swapping that with that, or with that with that. So, and I have to do the swap on this and on this at the same time. So if I swap those two and swap those two, it's the same gamma. And if I swap those two and I swap those two, it's the same gamma. And you could say you can do that generally by just choosing an arbitrary gamma and then adding it to the one where these symmetries are applied to it, and then this is automatically given to you. So once you have gamma having those symmetries, now you preserve this form, this one here, just because I've written these underneath. So apart from the factor, overall factor of lambda cross, these things are just the same pairing as we had before. But if you say we've applied the symmetry, which swaps those two over and those two over, then you preserve this form. So with the symmetry, as I say, swap those two, or swap these two and swap these two and it's the same, swap these two and swap these two and it's the same, then you get preserving both forms. So that struck me as rather peculiar, why you have to go to these strange coordinates, but after a lot of hard work and various other things, trying to do other things, it occurred to me you needed to do something very asymmetrical like this. And it's got to be asymmetrical 0, 1 and 3, 2 in that order because of something else. Now you see, you want to make the space-time real. You see, up to this point, I'm only looking for this in the sort of complexification, so you'd be looking for complexified solutions of Einstein's vacuum equations. See, when you choose that, preserve both these forms, I should make that point. If you preserve both these forms, then that gives you the vacuum equations. And to see that, it's best to look at local twistors, and you see that the preservation of the vacuum equations correspond to the preservation of these forms here. So it's something else that one has to look into carefully. Why that's the Einstein equations. But accepting that it's the Einstein equations, because the preservation of this form as a challenge is resolved by choosing these coordinates in this particular equation. So what you would do is you choose gamma, which has the symmetry, and that can be done explicitly, because as I say, even if you choose a gamma which doesn't have these symmetries, you should just add it to all the symmetries once applied, or I guess you do this swapping and that swapping, and then both at once. And so there are 4 different terms, add them all together, divide by 4, you automatically have a solution of the symmetry conditions that you need. So that's completely explicit and effective. And once you have that, you can then go back to what you need for the preserving the other form, which you really need that not just for the symplectic structures, but to give the thing in the geometric quantization, which gives you the non-commutative algebra that you want to go from one to another and make sure you preserve the algebraic structure. That means you need this form after all, but you can, having got this one, you can go back and explicitly get that one simply because, and I guess I have a little room to write down, you have this relation. This thing, I should say, has to have total symmetry, total homogeneity degree 2, so that if you think of z's and w's all together, and if you scale more up by some factor, kappa say, then phi goes up by kappa squared. Mm-hmm. But you have to think of the homogeneity as applying to both at once. And then that condition, if you write it all down, comes down to phi equals z alpha w alpha plus, well I should say 2 phi, plus curly z alpha, curly w alpha. So once you've got the transformation between the z's and the w's that you get from this, you can go back and construct phi, the old phi, and then you can go back and do the quantization stuff. So it's a little complicated and a little bit strange, particularly because this odd choice of coordinates here. Now the final point I want to make is that I've been playing with these things all in the complexification. You see, you immediately start by making your z's instead of z bars, and you say, okay, later on, when I've finished everything, I'll try and find the condition where w and z bar, w actually is the complex conjugate of z, and that gives you real solutions. And rather amazingly, when I looked at this strange set of coordinates here, this is what I refer to as the gift of the gods. If you apply this complex conjugate relation, it only churns around the ones at the top and then the ones at the bottom. It doesn't mix the top and the bottom. So if you have the complex conjugation relation held in here, and also there, for the w's, then you automatically get the real solutions. So you want a gamma which is Hermitian with respect to interchanging z0 with w2 and z and w1 with z3. And you can see it does it automatically, except for the slight irritation that you've got the lambda sitting there. So the Hermitian has a bit of skew Hermitianness to it because the lambda is imaginary. So these have to swap under the complex conjugation into each other, and these have to swap into minus each other. So you just have a strange hermeticity condition. But that automatically, because you've got the complex conjugates all on the top and all on the bottom, and they don't mix the z's and the w's together, which then you wouldn't know what to do, you see, but you fix them here and fix them here, and that gives you a space which is real. So you automatically, assuming that the theorems all work and all that, at least on a formal scale of things, it does seem to give you solutions, I should say generic solutions of the Einstein lambda vacuum equations. Curiously, the lambda is important here because it makes that into a non-degenerate 2 form. If lambda wasn't there, it would be degenerate, and no doubt you could do it all, but it would look much more degenerate and strange, and I want to have the lambda in there anyway, because I think it's important for twistor theory to handle the lambda vacuum equations. And I should say that in the old nonlinear graviton construction, Richard Ward had a way of doing it with the lambdas as an extension of what I had originally had without the lambdas, and this is simply a question of preserving this form here. And so that all is part of what we have here. So as far as I can see, at least at the formal level, it does seem to work. A lot of things need to be checked even at the formal level, and what's really the stumbling block at this stage is to make sure that the versions of the Kodaira theorem and things like that still hold, and how do you make sense of what you mean by small neighbourhoods and all that sort of stuff, which I haven't addressed here, but the sort of analytic part of it. I've done the sort of algebraic part of it. The analytic part of it might be tricky, and maybe the theorems are not sitting there to be used, or maybe they are. I don't know the answer to that. Thank you.